So now we will improve this in a solution to get something out. So let's take box input. So what this means, I want to give input like this, so which is f naught, and this is a, this is ta. So this is t, this is value. So this is equivalent to, I am giving two forcing. So first one is uh, u u of t, u of t, so the minus u of t minus a. So I have two loading. So if I do this, I will get this equation. So what I'm getting is, whenever I put, this is the input, when I give unit uh, step input, I will get unit step response. So whatever we have discussed, unit step function forcing, unit response of unit step function. So this is t minus a input force into the system, we will get response of t minus a. So this one is called a linear system. So now I'm using the system into this equation, k of x equal to f of t, which is the box input, which is f naught of, f naught is common, u of t minus u of t minus a, right? So now what I'm interested in, I'm interested in decreasing this ta to very small, decreasing this to very small, and ta into f naught product should be 1. So this is my conditions. If I do that, so first it will be here, so ta f naught, so ta into f naught equal to 1. So what I am trying to do, I am decreasing this and increasing the f naught. So this will be ta by 2, this one equal to 2 f naught. So then 2 f naught into ta by 2 equal to 1. So similar like this, I am increasing this f naught infinitely high and ta is small. So this is very high f naught. So some constant will be there. There is another constant, small constant, high constant. So multiplication of these two is 1. So that's it. So now I'm substituting it. So now I will get, so what the response I will get, I will, for this configuration, so I will, since the system is linear, I will get the response like this. X of t will be g of t minus g of t minus a. So now I am applying the condition of these forces. So what these forces condition says, so limit ta goes to 0 and f naught into ta, so there is f naught here, so f naught into ta goes to 1, x of t. So I'm applying, so limit here also there is a limit, f naught into ta goes to 1. So I have f naught g of t minus g of t minus a. So I'm adding, see, I'm taking ta in both numerator and denominator. So now f naught ta is 1, so this becomes 1, and this term looks like derivative with respect to t, right? So then this ta is the constant, very small constant in t axis, therefore it is this condition, limit ta goes to 0, f naught ta equal to 1. This condition leads to g dg by dt. So now this is very important result. So now let's look what this condition means. This condition means direct delta function. So what this direct delta function? So the direct delta function says, so at t is equal to ta, so this is t axis, so there is a one spike will be there, so in small time distance it will goes to infinity, the amplitude will be very high, the distance will be very small, so this is dt and say. But if you take the area of this signal, it will be 1. So this is called d of delta t minus a. So this is direct delta function. If you integrate it minus infinity to infinity t minus a into dt, you will get 1. So this is the definition of direct delta function. This delta t minus a equal to 0 is the equation. So what this means, whenever this t is equal to a, so it is infinity. In all other places it is 0, where t not equal to a. So that's the meaning. So, and there is another property, if you multiply with any function f of t into this t my delta t minus a dt, so you will get f of a, because at least only one point you will get the result, at all other points you will get 0. So now we need to find the response of impulse functions. So what we have seen, so if you give impulse function to the system delta of t minus a, x of 0 equal to 0, x dot of 0 equal to 0. So if you give him this one, so the response of impulse function will be dg of dt. So this is what we have seen so far. So now we will take derivative of g. So g is given by e power minus neta omega t, sorry, f naught by k, f naught won't come, 1 by k, 1 minus e power minus neta omega t cos omega dt minus neta by 1 minus neta square root sin omega dt. So now we take derivative, this is g of t. So now we take dg by dt. So we will take 1 by k, 1 minus, so we need to use uv rule. So cos means sin omega dt into omega d minus neta by 1 minus neta square root cos omega dt into omega d plus so this is, so we need to put some bracket, so minus neta omega e power minus neta omega t cos omega dt minus neta by sin omega dt. So now we take the derivative of this is g of t, so we will take the derivative of g of t. So this is the expanded version, so you go through this and then we collect sine terms, this sine terms and cosine terms differently. So we collected sine and cosine terms and we will try to simplify the terms, coefficient of sine and cosine. So where the coefficient cosine omega t goes to 0 if you expand it, and the coefficient of sine omega t, so if you do some simple derivation you will end up in this form. So now you substitute into this main equation. So yeah, this is the main equation. So substitute into this main equation, you will will end up here. So now, so you do simple modification, so then you will settle down into this equation, which is the response of impulse function or direct delta function. The first one, when eta is equal to 0, h of t becomes 1 divided by m omega e power minus, so this becomes 1, this is sine omega dt. So we will get the response of the amplitude 1 by omega m omega. So it will be like this with the period omega d, 2 pi by omega t, 2 pi by omega, so omega d equal to omega. So when the damping is not equal to 0, then so our then we will get the amplitude decay profile. So since this therefore this starts from 0 and it will go and it will end here. So therefore, and this one, and you can ask what are all the other things. So you can ask what are the other ways of deriving this same equation. So equal to 0. So let assume, so free vibration, there is no force in it. So what we are doing, so let's say there is a beam, so I am creating a boundary condition like this. So 1 by m of velocity is being applied. At that time the system is in 0 displacement. That means it is a quick impulse response. So when we give this, so let's try see what solution we are getting. X of 0 equal to a plus a is equal to 0, right? X dot of 0 equal to a0, we can leave it, so b omega d minus neta omega a0, yeah, other rest of the things also 0, equal to 1 by m, sorry, 1 by m. So therefore b equal to 1 by m omega d. So now if we write the equation x of t, so what we will get minus neta omega t. What is b? B equal to 1 by m omega d sine omega dt. Oh my god, we will get the same equation as that of h of t, so impulse response function. So that means, so we can give the impulse in the form of boundary condition. So that is the thing that we have to keep in mind. So we don't need to solve in straightforward way. So there are various other ways of getting this impulse response.